Thank you, sir. Now, it's a great privilege to introduce Dr. Manuel Ravishankar, currently working as a professor and head of the department in the Department of Mechanical
Hello,
Engineering.
Ravishankar sir. Good afternoon, sir.
He served nearly 7
Yes,
years
Professor.
as an assistant
Sir, shall we start the session, sir?
Yes, yes.
Right. Thank you, sir. Now, it's a great privilege to introduce Dr. Manuel Ravishankar, currently working as a professor and head of the department in the Department of Mechanical Engineering at IIT Tirupati. He served nearly 7 years as an assistant professor in the Department of Mechanical Engineering at IIT Guwahati before he joins in IIT Tirupati. He did his BTech from SV University, Tirupati, and MTech as well as PhD from IIT Kanpur. His research group focuses on micro nano manufacturing, sustainable manufacturing, precision 3D printing, online monitoring, biomanufacturing, coatings, tribology, and rheology. He has published over 110 internationally reputed journals and 150 international conferences, 7 patents, 5 books, and 25 book chapters. The knowledge transfer of his patents is already been transferred to India's leading research laboratory such as CMTI Bengaluru. Presently, he is having a 7.5 crore rupees projects as a principal investigator and 200 crore rupees projects as a co-investigator. He guided 10 PhDs, 40 MTechs, 50 BTech students, and guiding 7 MS and 20 PhD students. He is also an associated editor of Journal of Manufacturing Processes, Q1 journal with an impact factor of 6.1. He is the recipient of prestigious awards such as Institution of Engineers India Young Engineers Award in 2015, Indian Society of Advancement in Materials and Process Engineering in 2011, finalist of Indian National Academy of Engineering Young Engineer Award in 2014. He recognized as top 2% scientist across the globe. He is one among the top inventive Indian researchers. He and his students received numerous best papers, poster awards in national and international conferences. Apart from his academic awards, he also received Outstanding Sports Personality of IIT Kanpur in the year 2009. Really, we are great privilege for us as Mamila Ravishankar Garu has accepted our request to be an eminent speaker in this Atal FDP program. Thank you, sir. Over to you.
Hello.
Ravishankar, sir. Hello.
Ravishankar, sir.
Hello.
Dear participants, am I audible?
Ravishankar, sir.
I am Professor Audible, sir. Yes, sir, audible. Hello, sir.
Dear participants, am I audible?
Oh,
Yes, Professor. Audible, Professor.
yes, sir, audible. Okay.
Hello.
Yes, sir. Yes, sir. Yes, sir. Oh, oh. Okay, okay. Oh, okay, sir. Okay. Okay, sir. Now it's okay, sir. Yes.
Recording now.
Yes, sir. You are audible and visible, sir.
1 minute. The laptop system has moved some place. Remove here. There are some different ones. It is recording now. Yeah.
You are audible and visible, sir.
1 minute. Because in my laptop system, I removed some slides. I have to remove here. I forgot. Because some defense are there. Can you able to see my face?
Yes, sir.
Yes. Thank you.
Thank you, sir. Thank you. Please proceed.
Check my volume. Can you able to see my screens?
Yes, sir.
It's audible, sir. It's audible
Yeah.
and the slides are also visible. No issue.
Now the audibility is much better, right? Yes. Thank you.
Thank you, sir. Thank you. Please proceed, sir.
Because I was attending from the Mac system. So let me check my volume. Video.
It's audible, sir. It's audible and the slides are visible. No issue.
Now the audibility is much better. Am I right?
Yeah.
You can able to see in the full screen mode now. Thank you. Sorry for the inconvenience. Because I was attending from the Mac system, so it is creating
Yes,
some
sir.
issue. Where is my video? It was it would be my pleasure to discuss on the next generation. Okay, you can able to see in the full screen mode now. We range of cutting tools that we do. Can you able to see in the full screen mode?
Yes, sir.
Okay, thank you, Professor Samir and the management. And it would be my pleasure to discuss on the next generation cutting tools. What we work, we range of cutting tools that we do, ranging from micro machining, liquid cutting tools to semi-cutting tools. Because already you know what are the solid cutting tools and other things. In the liquid cutting tools, we have biological cutting tools, chemical cutting tools, and electrochemical cutting tools, and plasma, and so on, polymer rheological abrasive tools and other things. How we utilize these particular tools to address the various issues or various manufacturing processes and so on. Okay, so our area is same, but only thing is that how do you adapt for this particular? So we have various segments ranging from micro machining to the nano finishing group, sustainability in manufacturing, because nowadays we are closely working with the sustainable center, which we are getting at Tirupati. So there is one funding agencies where they're putting us on sustainability aspects and space and sustainability and so on. So one of the vertical that we work is a sustainable manufacturing, bio-nanomaterials and manufacturing, and additive manufacturing, smart manufacturing. We have different verticals where I have almost all 20 students who are working on various verticals. Since I'm going to talk on cutting tools, before I enter into the cutting tools, what are the other things that I will show? Okay, so we work on PVD systems. So this is to give you the glimpse, so that those people who want to join our group or want to get our assistance in terms of their PhD and other things. So it's not about only what we present to you. It's also we would like to utilize our facilities. So because we want to have the revenue generation model for self-sustainability of the machinery and so on. That is also, as the head of the department, I would like to give some emphasis on this one. The second thing, we have in coating systems, we have 3 systems. One is pulsating DC system, RF magneton sputtering. So in RF magneton sputtering, we have a single target one, and multiple target one. So for example, if you want to quote multiple materials and functionally graded materials and so on, you can do. So whatever you are seeing here is a RF magnetron sputtering where you have a substrate and target. So target will be bombarded, and you can see here have multiple target materials also. So when we want to make, we can make FGF stand for functionally graded materials or functionally graded coatings of FGC you can also say. And FGM also you can also say. Once you understand the surface morphology, we have multiple target materials also. So when we want to make, we can make FGMs. FGM stands for functionally graded materials or functionally graded coatings also. FGC you can also say, and FGM also you can also say. So once you understand the surface morphology, then you can also go for surface metallurgy and other things. Being titanium is a highly reactive material, at the same time titanium being a low thermal conductivity material. What is the good thing about it is that you will have a better transition layer. Better transition layer means you will have a proper bonding and other things. So once you put, you can also check with respect to elemental mapping and so on. So many of the mechanical engineers may not be well aware of elemental mapping here. So when you use SEM process or FESEM process, you have four optionals in EDS, energy dispersive spectroscopy. So in an energy dispersive spectroscopy, you'll have point analysis, line scan, area scan, and area elemental mapping. So what you can do here is that area elemental mapping. So once you map it, the complete surface area here, CL stands for coating layer, TL stands for transition layer. So then you can check how the elements are stacked. As I said, I have used the titanium material. On top of it, I have used the calcium phosphate-based orthopedic materials. So what I'm showing here, the pink particles. Once I coat all, once I do all elemental mapping, you can divide where the calcium particles are there, where the T particles are there, where is the substrate material, oxygen. Normally you don't take oxygen and other things, but however, we have taken looking at it's a highly reactive material. Okay, oxidation is a very uniformly it will happen. That's why we have taken oxidation indirectly, oxide film analysis. Okay. Anyhow, the material that we have taken is Ti6Al4V, so aluminum and other things. So here we have another tool, which is advanced tool that is called lasers. So if I want to do the machining, I can do the machining. If I want to do altering of any surface, I can alter the surface. Whether I want super hydrophobic, super hydrophilic, or lipophobic, or lyophilic, what type of surfaces that I want, I can manage. And that you can do by micro nanotexturing and micro finishing and all. So you can do by overlapping your laser beams basically. So beam is again one of the new generation tools. I cannot say it is fully a new generation tool, but however, when you are going to nanosecond or femtosecond or so on, for example, these type of lasers are predominantly nowadays coming into picture, and without much heat affected zone recast layers, these are can be textured properly. So that's why you can see here. So texturing can happen as per our requirement. Once only thing is that you need to play with respect to the overlaps of the laser beams and so on. Okay, so once you play with the laser beams, texturing and other things, and then you can coat the materials that you require for the orthopedic applications, then you can just look into the biocompatibility and so on. So whatever this you are seeing. So what do you mean by the biocompatibility that you are talking about is that whenever you are going to place this particular uh, implant inside the body, then for example, if you're putting a mild steel into the water and you're putting it in environmental conditions, it forms a rusting layer. Because rusting is an oxide layer. The same thing, for example, if you're going to put inside your body try to interact with respect to these particular surfaces, and this forms an intermediate layer that is called apatite layer, through which the proteins and minerals can be exchanged with the body fluids and so on. So that's the most important thing. That's why when you see in a artificial SBF and simulated body fluids, whenever putting it the in vitro conditions of the laboratory conditions, that you can express all the surfaces in terms of the apatite layer. Whatever you are seeing, the flower like of white layers is called apatite layer. That makes sure that this is a perfect surface for going ahead for the applications to the biocompatibility applications. That's why you can then move into the next arena of cell cultures using MG60 osteoblast cells and so on, which is not shown here because of respecting the time and other things. Then we have another solution where we try to do the biodegradable polymers for bioimplant applications. And these bioimplant applications is biodegradable. So we develop the polymers in association with chemical engineering of IIT Guwahati, not IIT Tirupati here at this point of time. So we do in situ polymerization as well as removing the impurities from the surfaces and so on. Okay, so then you can make the filaments and you can make the implants basically. So this room is not built in a day, means it's not that much easy to make as per the ASTM standards in a one go, because you need to play with respect to temperature, flow rate, molecular weight, and so on. So then we have optimized the conditions, optimize the melt flow conditions for which rheology plays a crucial role. And then we try to do the cancellous screws, cortical screws, tenement pins, staples, bone plates, and so on. The advantage of this one is you can put inside the body and you don't take out. So secondary operations may not be required. So there is another solution that we are working on. This is when there is a fracture, can I make implant? So always you cannot make implant because the structures of the fractures will be very, very niche. I mean, say micro or nano, and it's very, very complex in nature. This type of things one has to do, develop the rheological fluids. What are the rheological fluids? Because as I said, we mostly work on the polymer rheology and other things. So we develop thermosensible magnetic scaffold for bone tissue engineering. So what it means is, so you have a liquid at the room temperature about 25 degrees, and when you incorporate inside the bone fracture, it has to go to the nook and corners of the complex surface of the bone fracture, where you need not to have the staples or cortical screws, cascade screws along with the bone plates. And directly what you can do is, you don't require whatever the system that you are seeing here. There's a bone plate and screws are there. You don't require that. What do you know? You have a support from the flash, so that what you can do is you just push it bone fracture site, and liquid at 25 degrees flows, and your human body is at 37 degrees. So when it reaches to 32 degrees, it will form a adhesive film so that it can hold the male and female part of the body, and then it can do the at 37 degrees it become porous, so that it can have the bone autotomy from the both sides and so on. So what is the summary of this biogroup? What the summary of biogroup is, now we have polymers development, cells, and so on. So now we also venturing into the 3D bioprinting, and 3D bioprinter is already available at IIT Tirupati in my lab. So those people who are interested to work on, so many people nowadays are looking for the high impact journals and other things, and we are open. We means IIT Tirupati through proper channel. You can interact with us, and you can get the access for these machines, and you can use, so that the institute also benefit for serving you. And this is one of the niche area or the advanced area that we are going to talk or going to publish if you are interested in. So we have a machine called Luminex Plus, which is from Cellink USA. So those people who are want more details, they can just, I will show you at the end what are the facilities that we have. So we have Luminex Plus and Biomix also we are going to procure. So sustainable additive manufacturing, what we try to do is sustainable additive manufacturing is, so we make the plastic waste into a 3D printable solutions, which is common. I'm not saying this is no novel or something. So what we try to do is we try to make our own solutions for making a filaments basically. Okay, so I don't know whether you can see here. So you can tell us the composition we prepare, this type of compositions we prepare. Can you able to see the videos? So we make the whatever the compositions that you are looking. Okay, so what I mean to say is you can tell us the composition we prepare, this type of compositions we prepare, then we pelletize them, and this pelletization can happen, and then we are going to put, and then we are going to extrude the filaments. Okay, so here the good thing, biological hip implants, knee implant applications, here the good thing about this is many people are approaching us from various universities, various industries for their applications to make any type of filaments that may be for biological, hip implants, knee implant applications, liners, hip liners, and other things. So we prepare, you name it, we prepare it. Okay, so you want polylactic acid with carbon fibers, we can make polylactic acid with graphene, CNT, hydroxyapatite, copper, stainless steel, surgical steel, you name any material. Okay, so do your literature, come up with a novel materials that you want to fabricate your filament for your PhD work or to publish. It's not about PhD work or something, just also want to publish the work. So we can prepare you. We can prepare you as it's a completely commercial systems that we have from the Netherlands actually. So this is the final extrusion filament that you can see here. So this is just what we are showing you. He is here. This is the one. So we can make any type of filament that you can see, and you can see at the end what is this previously, where the particles are aligned and how the particles are look like here. Okay. Now at the same time, to give you more glimpse, scanning electron microscopy images of these particular things that you can see here. So this can give you a lot of information that we can also make microparticles addition, nanoparticles addition, and nanosheets, so on, whatever it's a graphene flex that you want to use, any type. If you want to do for thermal conductivity based filaments, if you want to do any type of filaments. Okay, so we are happy to provide as per the custom. However, as I said, Rome is not built in a day. That means that if you want the filament to be fabricated, this fabrication will have a lot of wastage because optimal composition will take a lot of time. Don't expect that today you have given and in a week time or 2 weeks time you are getting. So no, because we have a queue of things are there for our students' applications and so on. So at the same time, if at all I want to understand the melt-rheology of your composition, then first I need to do for rheological applications. We have to plot what are the melt flow conditions, and we have to see the loadings and so on. So these are all required for your applications and so on. Okay. So then we can try go and do for 3D printing. So we have 3D printers, commercial 3D printers, and some of the customers also asking us make the components out of it. Okay. So we are building so that what you can see here, the building is going on, and the final, when the building is completed, you can see the component. And we also do testing facilities, testing coupons, if for some companies for samples to check and other things. Some other thing that we also work is waste to wealth conditions. So porcelain powders, then we can make into dough. So we have two systems. One is AMS Hyrel system, which costs us around, as per today, the machine may cost you 40 lakhs. So that is Delta Wasps, which may cost you like, depend on your application, 20, 25 lakhs, 30, 35 lakhs, and so on. So these are things that you can use. And what is the novelty here? So when there is a waste material it's available, and there is a waste material available, just we, as I said again, we work mostly into the polymers. So polymer binders we develop, and these binders plays a crucial role in thermal debinding, chemical debinding, hydraulic debinding, and the sintering operations, because you need not have, or you don't want this type of polymer binders to be there inside these particular ceramic structures. As a site, it's always you can create beautiful structures, and these beautiful structures you can see what is the field rate, what is the rheological conditions, and so on can have, and then you can, once you optimize all these things, then you can make your own futuristic or complex component. Okay, these are the complex components that you can make, and any materials that you do. So what we try to do is we try to develop compatible materials. So our area is purely on development of some of the binders, because you cannot join the porcelain to the porcelain. That is a big problem because of the ceramic to ceramic. So we always try to have the binders for it. So it is not going to be that much easy. So one of our student, Palivella Bhargav Chandan, has done it, and currently he is at IIT Delhi after completion of his PhD. So we make binders. So you bring the raw materials, we make the binders for you, and we can print and we can show you the technology. And if you want, you can also go and patent the technology that you want. So as I said, let me start with micro machining. So I don't know how much time I have. I think I have another half an hour maybe. So sustainable micro machining. So we try to work on various aspects. One of the aspects is some micro machining.
My wish is up to 4:45
So,
with the question and answer session.
So, Professor, how much time I have?
Right.
Another 30 minutes?
Please start.
Yes, sir. Yes, sir.
Or
Yes, sir.
15, or 15 minutes?
Sir, actually,
Your wish is
up to 5, sir.
No. What is your wish?
my wish is up to 4:45 is okay, sir. With the question and answer session.
with
We
question and
planned to
answers.
conduct
Right.
the session between 3:30
So that
to
means
5
that I have to
p.m.
wind by 4:30. Am I right?
Please, sir, please.
Okay. So
Actually, the session will be up to 5, sir.
Convenient
uh,
time, sir.
So, but based on your interest, you can continue up to 5 also, no problem, sir.
Presentation, sir, and
no,
we
no,
will
no.
go for discussion session.
So we
See, I have
plan to conduct the session between 3:30 to 5 p.m., sir.
that is okay. So should I present up to 4:30 or 4:45 to take up the questions?
4:45 is convenient time for us, sir.
So 4:45 I present, am
You
I right?
start your presentation, sir, and we will go for discussion session. Then we will wind up this session, sir.
Because I have almost all 100 slides, so I don't want to teach all the things actually, because no, maybe it's time consuming. So micro machining is again, so DT100i, what is an intelligent machine. Whatever you are seeing is DT100. So we have a DT100i, which is intelligent machine that we have, which comprises of, you see, micro milling, micro drilling, micro turning, micro EDM, micro EDG, electric discharge grinding, micro ED milling, and micro lasers, simultaneous EDM, ECM. We have a lot of attachments. Okay, so you can see here the beauty about this particular thing is you can do whatever the small shaft that you want to make or electrodes that you can make for machines. Okay, so you can also make. So for this you require very sophisticated tools such PCBN tools, micro tools, whose nose radius will be less than 0.1 and other things. Normally, in a turning process of a conventional cutting tools that you can check. So what you do predominantly is that you will have a variety of cutting tools like what you are seeing is a triangular tool, cutting tool here. So the conventional way of cutting tool here is the TPUN 16030 These are the common cutting tools. So where T stands for triangular, okay. So T stands for triangular and 04 stands, I said that's TPUN 160304. 04 stands for 0.4 nose radius. Or TPUN 160308. 808 stands for 0.8 nose radius. Normally, nose radius as it increases, f square by 8r is your surface roughness. So your r will be in the denominator. As it higher and higher, what will happen? Your surface finish will be slightly better. So that works in the area of conventional manufacturing. When it comes to the micro manufacturing, whenever you want to do these micro features, if your nose radius is very high, so there will be a bending and offset problems that you can see here. So there is a bending and offset problems. To overcome that, what we try to do is latest cutting tools that we develop. What are the latest cutting tools is EDG. So our micro EDG we develop. So what I mean to say is one of the slab methodology that we can explain to you is just electric discharge grinding that we try to do. So we'll put a slab or a rectangular piece. Now I start because I have a rotation to the workpiece there. So what I mean to say is that because of electrical discharging and I'm rotating, there is a non-contact, and because of that you can make your own tool. Okay, so such shapes, whatever the shapes that you want to manufacture, you can manufacture array of the tools and so on. So these are the, if at all I want to make, I need to plan my process, I need to plan my cutting tools in a better way. As I said, so whenever I want to do certain applications, not only in a highly conducting materials, and there are applications which are coming in low conducting materials like silicon and other things. Wherever, if you want to go, you have to go for semiconductor applications and wherever sensor applications and so on. So if you see here, micro ED milling. Why I'm saying micro ED milling? Because you can rotate your tool. So otherwise, you can say only it is die sinking medium. That is also there. This is also is there. So you can do this thing. Okay, so that no. So if you go for simultaneous EDM and ECM, so what I mean to say, the electric discharge chemical machining or chemical micro milling. So but you can do EDM process, that is melting and evaporation at the same time anodic dissolution, because of which what will happen, the combination of that, which is patented by the micro tools with the electronic circuit. So this you can do the wonders. I mean to say that the surface roughnesses are much better. Now the what is the applications of it? The applications of it is whenever you want to mount some sensors on it. So if you use the first one, which is very, very rough conditions, so these rough conditions may hamper your signal because a lot of air entrapment will be there. When there is air entrapment, the signal to noise ratio will be, so noise will be very high. In a local language, if you says an element language, if you go for a better surfaces, what will happen is your noise levels will be very low, so that signal to noise level will be slightly better. Okay, so this is again a new way of understanding the problem. Okay, so the new way of understanding the problem is this. As I said, next generation cutting tools. This is one of the next generation cutting tools which are going to come by 2030 or 2040 or Vikashit Bharat 2047. You can just say. So this is the biological tool. So biological tool is, what is the biological tool here is, it is a cylindrical structure basically. I have not kept many slides about this one. I have only one slide. That's why your imagination for this particular thing is highly anticipated. Okay, so you can close your eyes and you can just imagine. So I have acidothiobacillus peroxidans, which are in the white, which we are getting from the source of supply. So then again, we have on other side copper, which is have a positive mask, which is, I mean, say photolithography. So you have photolithography that done that you can see here. I have one side acidothiobacillus peroxidans, on other side I have a copper plate on which photolithography is done. I mean, say I have coated and I have extracted the coated polymer layer in the required dimensions. The required dimensions here is micronozzle, or you can see at the bottom, it is micromixture. So now I have two entities. So what I will do is acidothiobacillus peroxidans. Acidothiobacillus peroxidans I need to put in a cultured medium and culture it, and I need to populate it. Once I populate it, I need to understand what is the life cycle of this particular acidothiobacillus peroxidans. When I want to understand acidothiobacillus peroxidans, so as why you need to understand the life cycle of acidothiobacillus peroxidans. In a layman language, I have a physical work of excavation using, assume that my own energy. I have three ages. One is 10 years child, 30 years young man, and 55 year person or elderly person. Who will do much better work for the physical work? Obviously, a 30-year-old young man can do a better job. So that means that I need acidothiobacillus peroxidans at their full potential. For that purpose, normally we try to understand the life cycle of acidothiobacillus peroxidans. So acidothiobacillus peroxidans, when it comes to the age of 19 to 22, 23, that is the young age. For that one, there we try to do put this particular photomask surfaces, and acidothiobacillus peroxidans will remove the material by the process called bioleaching. So How it will do? So it has acidulous for oxidants in the stomach region or inside the region. It is Fe3 plus. When it comes to the surfaces and interacts with respect to metal, and it converts to Fe2 plus and take out one of the copper atoms, and it goes inside and it converts into Fe3 plus again and again. So this is a circular process. I mean, say, like, we are not killing any organisms, like even Acidothiobasilus feroxidans, we are going to play with respect to the metabolism of Acidothiobasilus feroxidans. When we want to play with Acidothiobasilus feroxidans, just we are converting into Fe3 plus into Fe2 plus, and Fe2 plus go inside again, convert into the body metabolism Fe3 plus, so that it will generate like its energy. I mean, say glucose and other things when they break and other things. A lot of biochemistry is there, which I don't want to discuss now. So just bio-leaching understanding. Okay. So then you leach out atom by atom as per our required. So our required will be controlled by photolithography. Okay. So like you can see at the bottom, you have fantastically bio-micromixture. So where bio-micromixture, you have the surfaces, and the surfaces, eaten away surfaces, and you can see Acidothiobasilus feroxidans. At the same time, whatever the eaten away material or excavated materials or extracted materials are forming atoms or molecules or a bunch of atoms, you can say, or bunch of particles, you can say. So this will be the future. Why? So we are targeting, our UNO is targeting on a sustainability scale, zero waste manufacturing procedures or zero waste manufacturing processes. Here, if I want to develop this particular thing, I can develop by lasers, definitely, but subjected to the reflectivity of the copper, because laser is predominantly may not be used for aluminum and copper because of its reflectivity and other things. However, you can do the same by coating and other things. Okay, so that goes melting and evaporation, which is a waste for us. So indirectly, what I can say is, if I want to have a copper on a microfluidic structures and at the same time you want copper nanoparticles, you can extract both without wasting anything. For that, future is very bright. So those people who are interested to work, we are mostly looking for some people who works in these similar lines, basically. Okay. At the same time, we are happy to say that this particular paper has been got the first best paper award at IIT Madras. So we were surprised, in fact, because we got the first best paper award. There was the first place, second place, and third place, and we are very fortunate that we are thankful to IIT Madras for giving us first place for this bio micro machining, or the micro machining using microorganisms, which is the next generation cutting tools. So nano manufacturing, as I said, we try to work on some of the abrasive fluids, which you can see here. So chemomechanical polishing, which is highly reactive materials, designing of highly reactive materials, and then you play with the magnetic field, so that what will happen, chemomechanical magnetological finishing, so that what will happen is, one side you have MRF or MRP, you can say magnetological polishing, or fluid or magnetological fluid, that you can say. Predominantly the fluid will be like some oils, some surfactants, abrasive particles, and so on. At the same time, we will have some agents, which are chemicals, so that what will happen, this is chemomechanical slurries you can make. And since you have some CIP particles, which is carbonyl ion particles, normally 99% pure ion particles, will form the chain from the North Pole to South Pole, where the diamond particles or any other abrasive particles are entrapped, and just you have to finish it. So initially, the surface roughness is predominantly high. In the circumstances, you should always go for the high magnetic field intensity. That means, say that 1 Tesla or above 1 Tesla you can go, then you can just do the finishing operation. So as it progresses, what you can expect is that you can play with respect to electromagnet, where you can change to zero point 0.5 Tesla and 0.25 Tesla, or zero point 0.6 or zero point 0.3 Tesla. So that what will happen is your strength of the magnetic field intensity for the CIF central, what will happen is it lesses as the surface finish increases, or I mean say surface roughness decreases. You don't require high indentation values and so on. For that purpose, normally what you can extract is that initially you just go with 1 Tesla. So where your chains are much stronger, so the abrasive particles will have more support from the CAP particles. Like you see the basics of the grinding wheel grade and structures and bonding materials and abrasive type and abrasive size. In that circumstances, grade is how precisely or how hard you are holding the abrasive particle. So if you're going for the 1 Tesla, so your grade of the grinding wheel is hard grade. As you progress towards downside, or you may say 0.6 Tesla, so you will be having a medium grade. And when you're coming to the 0.3 Tesla, 0.25 to 0.3 Tesla, you're going to have a soft grinding wheel where you can do the batch finishing operation. That's why the beauty about this particular process is that you can get this process in situ. If you want to do the conventional manufacturing of grinding, you require 3 grinding wheels. One is hard grinding wheel, one is medium grinding wheel, one is soft grinding wheel. So however, you can play with respect to magnetic field, and you can play to this one. As you can see the surfaces, and people who are looking at semiconductor manufacturing, because now another 5 to 10 years, India is putting a lot of money on semiconductor manufacturing. This is a global world is looking at India for semiconductor applications and semiconductor manufacturing applications. So those people who are interested in semiconductor materials, semiconductor fabrication, semiconductor characterizations, and IIT Tirupati is one of the hub for testing of electronics. At the same time, you're also working closely with those hubs which are going to fabricate semiconductor materials and so on. Okay. So now, if you have time, just I'm going to show you the new tools that we have developed. So as you see here, surface finish is a big challenge in additive manufacturing. When you see additive manufacturing big challenge, so obviously you need to resolve it. So what we try to do is to understand the surfaces. So when you go for additive manufacturing, you require very complex surfaces, definitely, and you fabricate it by laser bed fusion, VAM, and so on. So here, what you can see here, if you see the surface under the scanning electron microscopy, you see the surfaces like this. So these surfaces, if you are going to use in the practical condition, it will completely destroy the system. That's why 3D printing, people, whatever the 3D printing that they do is a partial job. It is not a complete job. You need to do lot of post-processing technologies, or one of them is finishing process. Why you need to do the finishing? So you need to do the deballing. Whatever you are seeing, the spherical balls, it's called balling effect. You need to do the deballing effect. You need to reduce the roughness, and you need to reduce the waviness. And some people want very shiny surfaces, obviously, and some people want microstructure as per requirement. Some people want columnar, some people want spherical, some people want dendritic, so on, microstructures. Some people want very flat surfaces, and many people want less maximum peak to minimum valley. And some of the people may be asking you, or the customers ask you for some of the compressive residual surfaces. So as the world progresses, the complexity progresses and wishes of the human increases and the requirement of the customers will increase. So as a manufacturing engineer, you should be ready for always the new challenges that you are going to face. So, so what you try to do? What we try to do at IIT Tirupati is converting a 3D printed component into a practically usable form. As I said again and again and again, that the 3D printing, having a 10 crores machine, having a 20 crores machine, and a 5 crores machine, or any machine that you have, is a partial solution for the practical problem. It is not a complete solution. So if you print it, you have done 50% of the job. If you want to put in a practical condition or practical application, you need to do lot of things. Centering you need to do. Sometimes hipping you need to do, horizontally press. Then you need to do finishing. You need to do lot of microstructure analysis, so on. And you have lot of jobs to definitely. Okay. So what we try to work is use chemical, electrochemical plasma, dry electrochemical, abrasives, so lot of technologies that we have at IIT Tirupati, and we are happy to say that we are having one of the best facilities at IIT Tirupati in terms of converting a 3D printed component into a practically usable form. Okay, so just I will give you the glimpse of overview because I have another 5 minutes to wind up. So I'm not going to talk on abrasive based. I'm just going to close on abrasive lace based advanced cutting tools. The first cutting tool that we try to work is chemicals that we develop. So you just have to have the chemical technologies with the dynamic chemical technologies, static chemical technology that you can do here, and you can make your own applications for this. Okay, so you just put your components inside that you can see here before and after chemical polishing. So we design and develop the digital materials. So in terms of this one, my digital material is a chemical composition. So first, and I want to understand is metallochemistry. What is the composition of the metal or alloys or metal matrix composites and so on, whatever the 3D printed components that we receive. And we should play with respect to our existing knowledge on these chemicals. So that gives rise to some of the finishing processes, which is called chemical finishing. One of the predominant process in additive manufacturing is generating the lattice structures. The 3D printing companies and so on, people develop very, very complex lattice structures. But when it comes to the finishing of this one, it's very, very difficult. That's why one of the solutions that people uses is chemical finishing and dynamic chemical finishing and dynamic nano chemical finishing and so on. We try to use. So again, the second one is electrochemical finishing, or you can say electrochemical polishing. So you have to have a particular station where once you get the component, you need to degrease it, then you need to rinse it properly, neutralize the component. I mean to say any ingredients waste, I mean to say oxide films are there or something, you need to take out that, then you need to rinse again, then electrochemical machining, or you can say electrochemical polishing that you have seen, then hot rinsing, because you need to have different types of hot rinsing is required. Then again you rinse, then you get a product. That what you can see here. So initially the surface roughness was almost 9.763 after sandblasting. I mean to say plus, I can just say like 10 microns. So 10 microns to almost 0.6 microns, which is a big. I am just going to cut the big peaks and going to bring it into the required. That's what you can see here, fine surface, which is also. We have another one process. So now the question here is what we design. What we design here is, again, we design the cutting tools, which is called liquid-based cutting tool, which is called the electrolyte. Okay, so designing of the electrolyte for your metallochemistry is what is our expertise, or we try to develop for you. Okay, so we have another one setup that is called electrochemical plasma polishing. Here you can see the fire. So that fire is the plasma. You can say charged plasma. You can just see the gases are there, and so on. So what is here? It is a combination of EDM and ECM where you can get a spark at the same time electrochemical finishing, so on. So what is the beauty about this particular process is previous process. This is electrochemical polishing. You will have an electrochemical solution which is you need to throw. I mean to say electrolyte which you need to throw. So these electrolytes are sometimes compositions of chemicals. So disposing of these particular chemicals is very, very critical and complex. So that's why we opted this particular process. This particular process is electrochemical plasma polishing process. Electrochemical plasma polishing process where the salts are utilized. So the salts are utilized here, and you can see here it is disposing is very easy. 200 liters of water is there where I am going to put 3 to 5 kgs of salt. Okay, so disposing of this particular thing is not a big concern because we are within the limitations of the so-called government. I mean, say so-called the organizations, health organizations, and so on. So, what is the beauty about this particular process? You can see here, clustered additive manufacturing components. Also, it can give you a beautiful shine. That is, these are the tire mounts, serrations, and other things. It will give you a fantastic lustrous surface finish. Will be very good, and it shines a lot. So some of the examples that you can see, you see here, this is all finished by normal processes. Then electrochemical plasma polishing gives you very, very beautiful shining. That's why you can go into the market for selling these at very, very economic prices. Okay, you can see the bone plate at the bottom and the things. One is not shining, another one is shining. However, if you see the surface roughness values are approximately same. So there is no much difference in the performance, but there is a high difference in the perspective. So when you are purchasing for biomedical implants, the perspective of the human is also plays a crucial role. That's what. Okay, so with this, I am very thankful, and yeah. So if you have any queries, I'm just going to show you the facilities available. These are the best facilities that we have. And let me tell you, we have metal additive manufacturing, ceramic additive manufacturing, polymers, post finishing, 3D surface parameter from Bruker. We have IDDM, we have from Miguel Charmelis, which is world one of the best DMG Mori milling and lathe. We have high speed cameras and IR cameras, micro nanoindentor, XRD. We have CMM out of furnace tester, PVD, as I said, RF macro sputtering, single target and multi target, and pulsating DC. We have tribometer, which we have rotary, reciprocating, and butterfly motions. Some of the facilities arrived: 3D filament making, micro machining center, laser micro machining center. These are all 1, 2, 3 we have received. EDM, die sinking EDM, which we are about to get. FESCM with EBSD, EDS, and lithography, which we have just reached. Installation is due, as per my understanding. Atomic force microscopy, which we are going to get in a couple of months. PPMS, physical property measurement system, which is a very, very expensive machine, like 18 crores, which we are going to get. And XPS is also is in the order. HRTM is next gen Next year, we may be getting high resolution transmission electron microscopy. LIBS, we have already laser-induced plasma, breakdown plasma spectroscopy, which we have. It is one of the type of spectroscopy. DSCT, GATTA, we have incubators and so on. Pre-fatigue testing, friction state passing, and other things. We are open for summer interns who can come for long durations, like 5 months to 6 months. And being a young generation, we don't have accommodation now. So if you are interested and if you can handle your lodging and boarding, we can give you research space, consumables, and so on, so that combined your institute and our institute can publish postdocs. We are looking at some project work. If you are want to execute at IIT Tirupati, like BTech project, MTech project, PhD projects, we are most welcome. So with this, I solicit your great support to support our journal, where our acceptance ratio is less than 10%. So I handle micro, micro and nano and abrasive manufacturing, rheology, tribology, and so on for this particular journal, Journal of Manufacturing Process, which is a SCA index Q1 journal with impact factor of 6.1 to 6.2 ranging. And I also thankful to all the funding agencies starting from IIT Guwahati for 5 lakhs, Water Research Center about 23 lakhs, then DST nearly 1 crore, DRDO about 75 lakhs. DITI, which is now Mighty Ministry of Electronics and Information Technology, about 60 crores, then 3 plus 3 crores from IIT Kanpur and ISC Bangalore for imprint program. These are all I completed at IIT Guwahati. Then I moved to IIT Tirupati in 2019. So I concluded this project from ACRB for 45 lakhs, BIRAC about 42 lakhs, ACRB 32 lakhs, and IGSTC, which is a big project, about 6.8 crores. These are all completed now, and ongoing are ISRO project, DST, STI 61. I have a small project 26. Mostly I'm concentrating on DRDL. We have a DRDL about, I think, like 16 lakhs we have. Whatever I'm showing is 17 lakhs here, over 42 lakhs. Power grid and other things. Yeah, we have one center for 120 crores. With this, another one is the students who are working tirelessly. I'm just front face guide. Thank you. And if you have any queries, suggestions, I'm very thankful to take up. Thank you.
First one you do, man. Sir, thank you, sir. It was very informative as well as illustrative session. Now I request participants to ask questions, if you have any.
So my name is QIS and I'm as a professor in mechanical engineering in GEC Kerala. So you mentioned something about laser texturing, sir. Good evening, sir.
Yeah, please introduce yourself and you can ask the question.
So my name is Vipin V. Pavan and I'm assistant professor in mechanical engineering in GEC Kerala.
Yeah, please.
Sir, you mentioned something about laser texturing, sir.
Yes.
Sir, I'm currently working on biodegradable implants, improving its corrosion resistance.
Okay.
So, for that, if we do texturing, can we control the corrosion, sir?
Yeah. You can, I think. I don't know what is. God. Can you repeat again? My mouse is just stuck.
Sir, currently I'm working on some coatings in this zinc alloys, magnesium alloys, for improving its corrosion resistance, for using it as biodegradable implants, for removing, avoiding this revision surgery and all. So this laser texturing can I use as?
You are using the magnesium alloys as your workpiece material, am I right?
Yes, sir. Yes.
So magnesium is a highly reactive material, and magnesium is a flammable material. Above 50 degrees, it will catch fire. So lasers is nearly a difficult task for you to use that things.
Okay, sir. Okay.
Any other material, if you can say, then I can help you.
Okay, sir. Also, sir, some of the finishing methods like like you mentioned about 3D printing, post processing, finishing process. If we are, can we use that for the oxide coatings we are making on some magnesium alloys, zinc alloys? Can we use that method for finishing that also, sir?
Can you repeat again?
It is like a micrometer level coatings if we are making on some metallic substrates. Can we tailor the porosity using this finishing techniques? That is my doubt.
You cannot do the, see, the existing surface, you can finish it. So you cannot generate the porosity. If at all you want to do the porosity, again you have to go for porosity. You cannot do. You can do some texturing on the surface. So as you were asking in the previous condition that can I use lasers for magnesium? Rather than lasers, you can use some mechanical methods.
Micro machining techniques.
No. Simple techniques. For example, you take lathe machine, you know how to do knurling operation. Take the implant in a cylindrical shape and do the knurling. Mechanical texturing you have done. And you can get a paper out of it. Am I right?
Okay, sir. Right.
Only thing is that, so we should have a thought process. Simple thought process on a magnesium. That we have done already. That's why I'm saying you.
Sir, okay. It was a very nice session, sir. Thank you for the informative session.
Yeah. So the last session, all people are tired.
Good evening, sir.
Yeah.
Myself, Dr. Natrananda Behra, teaching in QIS College of Engineering Technology, Nangul. Sir, how can AI and machine learning process to optimize this parameter in coding process?
I am very poor in AI and ML. I use my own intelligence. I don't have much artificial intelligence in me. So I I need to learn. I don't know how to use AI. Till now, I never used the AI.
So, what are the method to find the adhesion strength during the coding process?
Adhesion strength you can do. So adhesion strength you can do using scratch test basically. So what do? Assume that you have this particular surface. You just coat on surface. Now we have coated. Assume that in my study you have titanium, on top of it hydroxyapatite is coated. So you do a scratch testing. Scratch testing you can do by multiple means. One, you do the load ramping and you do the speed ramping by keeping the load constant, speed ramp by keeping the speed constant, load ramping. Ramping means increasing. So you will get scratches. Obviously, different scratches you will get. So put under ACM, go for the EDS process, elemental analysis that I told you. So energy dispersive spectroscopy. You just compare with respect to the surface, inside the scratch and outside the scratch, the plane area. Assume that this is my scratch. These are all my parent material. So here I should be able to get calcium phosphate. Here also inside the scratch, if I'm getting calcium phosphate, that means that coating is intact. If I'm getting a titanium there, that means that it is gone. Delamination has been occurred. So like that, you can do the scratch text. So standard protocol is that one where you have a DUCOM EMS, I think TR101 or some setup is there that we try to use a IIT Guwahati for that one.
Sir, can you do it in cross section, sir?
See, I am putting on the surface.
Surface or cross section, sir?
No, why you do on the cross section? You do scratch test on the surface. See, my coated surface only I will use, na? If I do like this, Inside it is a parade material.
But sir, thick coating, is it possible for a scratch test?
Thick coating means how much? What do you mean by thick
200 to
coating?
300 micrometers.
How much?
200 to 300 micrometers.
No,
Then
you don't get for 300, 400 microns. You cannot get that much because normally this micro nano scratch test will go up to certain only. So normally these 200 to 300 micrometers on bio implants is very, very expensive. You cannot use that much costly affair because if you see even cutting tools also, you will have few nanometers. There are 5 to 6 layers, titanium nitride, some bonding layers, and other things. 4 to 5 layers will be there. All layers will be nano only. So if you are coating like micro, I never did it.
okay. For the micro coating, you can go for lithium universal testing machine.
Universal testing machine. How do you do the bonding strength? See, I have a substrate on which you have coated. ओके आप इधर देख रहे हैं ना, ये मेरा सबस्ट्रेट है, ये लाइन है, लाइन के ऊपर ये है. आप इसको मैं खींचूंगा तो उससे कैसे पता चलेगा कि मेरा
If you do the all side coated, sir.
all side coated?
All side
Then,
coated.
all side coated, then you pull it.
Yes.
I
Is
don't
it
know.
possible, sir?
I don't know because I never did it. So I have to go through it. Normally we do on one surface. Okay, so all side coated, it may not give you a good results. Definitely adhesion strength will not be. There are standard protocol for us is scratch test as per the guidelines of the ASTM. So we follow the ASTM. But you may be right, you may not be right. I also don't know because I don't have answer for it.
Okay, sir. Thank you, sir.
Thank you, sir. Thank you for your great session. And thank you for accepting our invitation to be part of this ATAL FDP. Dear participants, any more questions? We organizers are part of this community. We thank you for. Okay, then. Thank you, sir. Thank you for your great session, and thank you for accepting our invitation and to be part of this ATAL FDP program. We organizers and the part of this community, we thank you for being the resource person for this session, sir. Thank you. Thanks a lot.
Thank you, Professor. And thank you all the participants. And if you have any doubts, I have projected my number and other things.